So today we're going to talk about chapter 1.2. We're still in the review area, so we're not going to go into a lot of detail. Just go over some basic stuff. Now, back from algebra and trigonometry and pre-calculus, that kind of thing. So first let's remember the most basic of functions, the linear function and their slope, right? A linear function is something that is like a line. Such as, for example, f of x equal to 3x plus 1, a very simple function. So you have a function like that, and that's a line. And to draw the line, you plot points on the Cartesian plane, like so. So we have, for example, for this simple function, for a linear function, you only need 2 points normally. Like what happens when x is 0? Then f of x equal to 1, so you plot 0 and 1. That's your first point. And another point would be, I guess x is 1 then. And then f of x is 3 plus 1 is 4. So when x is 1, y becomes 4. So you have something like this, extending both sides infinitely, and that's your linear function. And remember, the line doesn't stop here, okay? We just stop drawing it. But the line goes on forever in the same slope. So anything like this is a linear function. An important point to remember about the linear function is the slope. The slope is represented by the letter m. I don't remember why, but that's what everybody does, so therefore you're going to do the same thing. So the linear function is defined as, the slope is defined as y minus y1 or y2 minus y1 over x2 minus x1, where x1 and x2 are 2 points, any 2 points, okay? Then you just pick on, so you have x1, y1, and x2, y2. These are any 2 points on the slope, like the ones we just used to draw the thing, like when x is 0, y is 1, or when x is 1, y is 4. Here's the example. When x is 1, oops. When x is 1, then y will be 4. Then 1, y is 4. Okay, now for this particular linear function, you have a slope equal to, you pick something to be y1, y2. Which one is y2? It doesn't matter. You just need to be consistent. For now, we'll just call this x1, y1, that one x1, y2. You can, if you exchange it, it'll come out with the same answer because of the division in the formula. Anyway, so to follow the formula, you have y2 minus y1. 4 minus 1 is 3. And then x2 minus x1 is 1. So the slope of this thing is just 3. And there is, which is the same number here, because there is a slope formula that says that would be true at some point. Sometimes, okay, if the formula is simple. If it's not simple like that, when there you don't have a number in front, when this is just y, f of x equal to y, and that's just, everything is pretty straightforward. But anyway, generally speaking, you have, that is the definition of slope, and this is also written like this: delta y over delta x. The word delta, this is a Greek letter, it's not a triangle. The delta means change. Okay, so y changed from y1 to y2, and x changed from x1 to x2. The proportion of change is the slope, and is constant for a line. It's not when it's not constant, then that's when calculus becomes very interesting, right? And when it's constant, you're still in algebra. So that's where we're in right now. So that is the symbol, and this is one thing. Okay, remember, this is not 2 variables or anything. The delta y is a thing, like Annabelle. Okay, is one person. delta y is one symbol. It is not two I mean, it's one item. It's not two variables. So and it represents this, the difference in y versus the difference in x. And of course, the delta y is different depending on which points you're calculating from, but the proportion will be the same for a straight line, because the slope of a straight line doesn't ever change. It is constant and fairly simple. So then we have the slope-intercept form, which is f of x equal to mx plus b. Okay, I'll just show it to you on the screen here. I hope you can see it. Anyway, doesn't matter. You have the book. So f of x equal to mx plus b is the slope-intercept form, and then the slope, of course, is y2 minus y1 and x2 minus x1. Similar to this formula of the slope, you also have a different form. No, that's not the fx equal to mx plus b isn't actually we don't care what it is, what it's called. The point is, there's another way to write this formula in general. In general, you can write down the equation of a line with this particular m equals to y minus y1 divided by x minus x1. In this formula, y and x are the variables, whereas y1 and x1 are the numbers. That is of a specific point that you're using. But it doesn't matter which point you're using, this will come out with your formula for the line. All right, let's see. Okay, let's get out of here and do something else. Next. This is called the point slope form. Okay. It doesn't matter what it's called, to me anyway. And then, of course, the standard form of a formula is just ax plus by equal to c, where a, b, and c are numbers, whereas x and y are not your variables. A quick example that I can make up is, let's say 2x minus 5y equal to minus 100. Okay, let's come up with a 0.1. Let's make up an inconvenient line that we're not going to do anything with. But that's just, C is some number, any number, and so is A and B. This would be some kind of line. All right. Now the way to handle linear formulas is that sometimes you might have to, you're giving 2 points, x1 and x1, y1, x1, y2, and then you're supposed to find the slope, which we have already done. So we will go past example 1.12 and move along. So, right. Next, let's get out of the lines, okay, and go to something slightly more interesting. The lines where it has only x in the power of 1, because that's why you don't even see it. But the polynomial is more interesting, where it has power more than 1. A polynomial is something that has x to the power 2 or 3 or whatever. The standard polynomial is written like this. F of x equals to an to the x power n plus an minus 1, x power n minus 1, and so on, all the way down to a1, x1, and then plus some a0. Now, do not let this notation confuse you. This might look like a lot of symbols, and people tend to get blown away by symbols, like reading Russian when you don't know Russian, you know. But if you know what it means, it's not near as hard as it looks. You know, the Russian that you can understand might just be a shopping list. Just because you don't understand it doesn't mean it's difficult. In this case, the an are the numbers, and x to the power n are whatever power that your polynomial is. To make one up, and one such polynomial that we can think of, that we can make up, would be, say, f being the f of x. We're using f of x, so we'll use that for now. So for example, you can have this one right here. We had f of x is 3x plus 1. That's one polynomial, where n just equal to 1. So you only have this part, okay? And then a1 is 3, and then a2 is 1. So that's your first polynomial. So these are the an's, n minus 1, and so on, are the numbers in front of the x's, and the x to the power n is how high of a power your polynomial is. Next one, let's look at a slightly more complicated example. F of x equal to, let's say, 2x squared, okay, plus 5x minus 17, let's say. Now, in this case, the an, and in this case, n equals to 2, because that's the highest power for your polynomial. And so a2 is 2, and then it goes down by 1 at a time. So it goes to n minus 1. So, and then this is a1, which is 5, and then a0 is minus 17. So this, in other words, this is just a shorthand that represents all polynomials of any power. And let's come up with another example. I'm just making this up, okay? You can make it up too, it's just some random number. Let's say we'll have x to the power 4, and make up something else, 20, x to the power 3, and then 0, x to the power 2, and then minus 5. So this particular polynomial, oh, I forgot this part, minus 5x plus 0, okay? So in this particular polynomial, we have the highest power is 4, so n equals to 4, okay? And then, so a4 is minus 15, a3 is 20, a2 is 0, so normally you don't even write this because it's 0. And then a1 is minus 5, and a0 is 0, which normally you also don't write. But I write it out to give an example of what this thing means. So this formula basically represents all polynomials. And it doesn't matter how long you go. You can go a couple thousand or something. Well, nobody does, but you can. But the idea is that whatever your n is, you know, your polynomial may be extremely large, I mean, in size, or just a small, simple thing. It doesn't matter. This particular thing represents all those things, all those polynomials, and that is how it's written. Now, polynomial that has a power 2 is called a quadratic equation, which is very commonly used in algebra. The polynomial has the third power is called qubit, and we don't care that much about that. Well, at least I don't. So next, let's look at what is a power function. A power function is a polynomial that has only one thing that looks like this. F of x equal to ax to the power b. Well, okay. So a power function, well, anyway, that's anyway, so this is a power function is just something that has just one of these things, okay? And the fact that it's called power function is not that interesting to me. So then sometimes a power function can be even. Even usually means it's symmetrical. And then sometimes it is odd. If it has the property of, if you slap in a negative function, then a negative number, then it equals to the negative. Yeah. Let's move along. I don't find that to be particularly interesting. So let's move along. Next, the behavior at infinity of polynomials. Okay, the behavior of polynomials at infinity is that they will go to infinity. Okay, generally speaking, there are two kinds of polynomials. They go to positive infinity or negative infinity. By the way, generally the polynomial has two kind of shapes. One of them is look like a bowl. Those are the ones with odd powers. Even powers, like the quadratic equation, right? It looks something like that. If the power is higher, then the bowl becomes narrower. It gets narrow because it rises much faster. And the ones with the odd function, like if the highest power, if it's 3, then it does this crawling thing. Basically, part of it got, well, no, never mind. The point is the graph goes something like this. It goes down. Part of it goes down and part of it goes up. So this is for the even functions. Well, not even functions, but this is for the ones with even even, yeah. When n is even and when n is odd, then the graph looks like that. All right, let's move on. Next, the zeros. Okay, the zeros are fairly critical for polynomials, and that's when they are mostly used. So let's look at the zeros. Zeros are slightly more interesting. The first most important zero you can find, of course, is the quadratic formula, which I will just show it to you. Is being that you're in calculus, you really need to be able to memorize the quadratic formula in your sleep. Why? No reason. It's not particularly useful, but it's a matter of principle. You're in calculus now. You need the quadratic formula is one of your reasons of existence. The quadratic formula is minus b plus or minus square root of 4 b squared minus 4ac all over 2a, right? Right, see? So that's, and you need to be able to spit it out. Otherwise, why are you in calculus? You don't even know the quadratic formula in your sleep. Doesn't make any sense. So knowing the quadratic formula, which means you can find the root of any quadratic function at that point. This rule only applies to quadratic formulas. For higher polynomials, the story gets the root finding can get much harder. So, but we're not going to care about that for now. Most of the time, for the higher function, you try to factor it and reduce it to at least a quadratic formula, preferably a bunch of linear functions multiplied together, and then you can hunt down your roots. So, for example, should we do an example? No, let's not. Okay, let's do an example of a cubic function. How do you find the root of something? Here's a quick, easy cubic function in the book example 1.14. Okay, so let's look at this cubic function. Very simple cubic function. Cubic means the highest power of x is 3. Right? Let's see, so minus 3x squared, okay, minus 4x. All right, that's your cubic function. It conveniently doesn't have a last number to make life easy for you. So how do you do this? Well, you normally factor in, just take one x out, because everybody's got an x, you factor and take one x out, and you have x squared minus 3x minus 4. Okay, so you have that left. And then next, this is quadratic equations, or this is a quadratic. It's not, well, anyway, so then you do this, and then you come up with something, okay? There's x, so you need to have two numbers that multiply together to be -4, but added to become -3. And that would be -4 plus 1, okay? Because -1 times -4 is -4, plus 1 minus 4 is -3. So that's your, and so then your x's has to be your x's, oh, the zeros, which is what we're looking for. So the zeros are zeros, okay? X equal to 0, and then x equal to -1, and then x equal to 4. Those are your 3 zeros, and it only has 3 zeros because for any kind of polynomial, the number of zeros it has is exactly its highest power, or called degree. All right, and they also want to know what happens as x goes to infinity, I guess. All right, fine. So for that, as x goes to for all polynomials, as x goes to positive infinity, and being that this power, you only look at the term with the highest power, that this one is positive. So then, and as x increases, it will dominate all other things, and then becomes positive, goes to infinity. And similarly, when x goes to negative infinity, this one will be dominating and also go to negative infinity because it multiplies itself by 3 times, so that the negative signs survives, and so then f of x follows down the path of negative infinity. So that's how that part is done. All right, let's move on and see if there's anything more interesting. Well, next, we will skip over the mathematical models section, being that we're only doing reviews, so the mathematical model is not that interesting at this point. Let's move along to the next part, where we talk about algebraic functions. Algebraic functions are just some function that is not really much of a polynomial. So we have, such as, for example, the rational function. The word rational means ratio, that is fractions, or the root function, which you take a square root of, or cubic root of some other kind of root. Now all right. So to find for rational functions, the concern is always the domain. Sometimes the range, but mostly the domain. And the reason is because rational functions, the domain can have a problem when the denominator approaches 0. So you have to be careful about the domain when it comes to rational functions. Now let's look at example 1.16. So example 1.16, you have f of x equals to 3x minus 1 over, what is that? 5x plus 2. Okay, now the only thing that really matters here is the 5x plus 2 cannot be 0 because denominators cannot be 0 for anything. I mean, ever. So then the domain is all numbers where f5x plus 2 is not 0. So you just need 5x plus 2 not to be equal to 0, which means that I need 5x plus 2 not equal to 0. Okay, so then x will be, you solve for this, move the 2 over, becomes minus 2. Move the 5 down, becomes division. And so x cannot be equal to minus 2 over 5. Otherwise, it's fine. Okay, anytime x is not minus 2 over 5, you're good. The range can be basically anything, because it's just a fraction. So if you add some kind of a number on the side, whatever range you choose, you'll be able to solve the equation. And then you will have you. So the range is, well, the range is all real numbers. So then that's that's what we are going to count as the answer. All right. Now moving along. The next example, find the domains of more functions. Okay. Next, let's look at part of example 1.17. For example, you can look at the function f of x equals to some square root, 4 minus 3x. All right, so that's a root function, right? So as a square root, to be exact. Now for all square root functions, you have to remember that you cannot take the square root of a negative number. Therefore, so all numbers here has to be positive, bigger than or equal to 0. So the domain is defined as this thing has to be bigger than or equal to 0. So 4 minus 3x has to be bigger than or equal to 0. So then you move the 3x to this side, it becomes positive. 3x bigger than or equal to 4. And then you have, 3x less than or equal to 4. So x has to be less than 4/3. And that's your domain. As long as x is less than this value, then you're okay. If x gets bigger, you're taking the square root of a negative number and doesn't exist in the real number system. All right. Let's see, moving along. Next, we'll look at so-called transcendental functions. Transcendental functions are something that is just, what's so transcendental about it? Well, it's not just the ABC. There's some specific manipulation of the function. For example, transcendental function is, one example would be the trigonometric functions, right? Which is like the sine, cosine, tangent, and all that stuff. Okay, but not just trigonometry, another transcendental function is the logarithmic functions, such as log of something. All right, now, having said that, let's move along. If you don't remember what the transcendental function is, you probably won't die for it. Next, piecewise functions. The piecewise function is simply a function that has two different definitions because it is a combination of two algebraic equations. Like a quick example would be f of x equal to, let's say you have an f of x that's piecewise. You have a chunk of it when x is less than 0, it's minus x. For x less than 0. And then for x that's positive, it becomes x. For when x is bigger than or equal to 0. All right, so as you can see, basically it got pieced together. You have these are both linear functions. So you have two lines, and two lines together define the f of x. And each line only defines part of it. Like this line defines for when x is less than 0, and this line defines for when x is positive and includes 0. So to draw this function, we need to look at this thing. Okay, here's your Cartesian plane. So when x is less than 0, f of x is minus x. So when x is minus 1, y is positive 1. So it's something like this, right? It goes, when x is negative 1, y is positive 1. So it goes like that. Whereas the other one, when x is 1 over positive 1, y is also positive 1. So it goes like this. So there is your graph. Piecewise functions are not particularly exciting. It just means the function has two separate definitions, need two or more definitions, because one algebraic formula isn't going to cut it, but two will do a fine job. So that's that. And then, so next, let's talk about function transformation. Transformation just means you add something or subtract, or you move the graph up and down the plane. As an example, for transformation is, for example, let's say you have the simple function, quadratic function of f of x equal to x squared, okay, which is just your regular thing, right? I won't draw it yet. So then, but then the question is, what if you get, how does that compare to f of x equal to, say, x minus 2? Well, the two functions are such that it just got moved, that's all. So let's say that your initial function is just this thing, okay? And the parabola. Well, the new function is the same graph, but you have to yank it some way. So when x is 2, y is 0. So when x is 2, y is 0. So the new bottom for the new function is over there. I will use a different color to indicate that fact. So for your new function, when x is 2, y is 0, so the bottom is here, but everything else stays the same. So you imagine you take this thing, you shove it over 2 units, and it looks like this. Okay, so it's identical except it got moved over. So that's called the transformation. There are other ways to transform it, like instead of adding a number inside x, you can add it outside or something, and then it moves it up and down and so on. A vertical shift. But we're not going to go over that. That's enough transformation for today. So let's move on. Let's see. There is also, but for this kind of transformation, the graph shape doesn't change. But there's also a way to transforming it where you stretch it. The shape does change in the sense that it got stretched or compressed. That's when, for example, when you multiply x with something, such as how does f of x, if you add a 2 here, put this away. So if you multiply x squared so that it becomes 2x squared, then how would that look? Well, it would just be more stretched. But we're going to skip the stretching for now and move on, because I want to get through the revision chapter so that we can get to calculus, right? We shouldn't be stuck in revision forever. When are we getting to calculus? Anyway, so moving along. So there is a transformation graph, which is good to refer to sometimes. I don't think it's necessary to memorize this thing. You just, if you're not sure, you can just use a simple equation such as x squared, and then do the transformation and figure out which way it goes. That's all. So, moving along. And that's the end of chapter 1.2.